This video is for the revision of metallic bonding. So metallic bonding is the electrostatic attraction between lattice of positive ions such as sodium. Okay, I'm going to draw 6 sodiums here. And they are attracted to the delocalized electrons. So I'm going to draw 6 as well. So I randomly draw the electrons. This is the cloud of electron or the sea of electrons. And the attraction between these positively charged ions here with the delocalized electrons, that is metallic bonding. How strong this metallic bond is going to be, it's going to depend on the charge of the ions here and the radius or the size of these ions. Okay, I'm going to draw one that is charged 2+. Since the charge is 2+, I'm going to draw 12 delocalized electrons randomly. Since there's more attraction here, therefore, compared to this attraction, it's less. So, which is why if the charge is higher, you'll get stronger metallic bond. If the charge is lower, you'll get a weaker metallic bond. Okay, if I have something with a larger radius, an ion with a larger radius here, the nucleus would be deeper inside and further away from the electrons that are delocalized. Compared to the small one, the nucleus is quite near to the delocalized electrons. So this attraction here is stronger, while this attraction is weaker because it's further away from the nucleus here. And the nucleus is the one that is positively charged. The protons are there. So therefore, if the radius is larger, metallic bond would be weaker. If the radius is smaller, metallic bond would be stronger. Metals are good conductor of electricity because of this delocalized cloud or sea of electrons here. So the electrons are mobile, they can conduct electricity. Generally, metals have low ionization energy because they want to imitate the noble gas electronic configuration. So they will form a positive ion. So such as sodium, it will be 1s2, 2s2, 2p6, and that 3s1 is the one that was removed and it went into the cloud of electrons, it was delocalized into the sea of electrons. So it will form an A+. Metals are very flexible, as in they can change their shape. They are malleable and ductile. Malleable meaning you can press it into sheets, and ductile meaning you can pull it into wires. The reason they can do that is because the force of attraction between these positively charged ions with those delocalized electrons, they're in all directions. So that is why they are so flexible. So when you apply force here, see it just slide over each other and dislocate like this, but there's still attraction between the positively charged and the delocalized electrons here. Whereas if you compare that with an ionic lattice structure, if we apply force, then it will dislocate this way. And you might see that the negative is facing the negative and the positive is facing the positive. This makes it brittle. Whereas metal, they're just attracted in every direction because the electrons are everywhere. It's delocalized randomly. These makes metals malleable and ductile. Okay, they've got high melting or boiling points. The reason is because metallic bonds are very strong. Group 1 metals have lower melting point compared to group 2, and transition elements have higher melting point. The reason is because they've got stronger metallic bonds. If we compare the trend of the melting point across the period, we'll see that the melting point increased. The reason is because the metallic bond got stronger across the period. Let's see some examples like potassium, calcium, and a transition element. So let's compare potassium and calcium first. First of all, potassium only delocalized one electron into the cloud of electrons. Compared to calcium, it delocalizes 2 electrons each atom to the cloud of electron to form a 2+ ion. Okay, therefore, this causes the metallic bond to be stronger in calcium. The next reason is because calcium is also smaller. Calcium 2+ is also smaller than potassium plus. So because it's smaller, the attraction is stronger between the positively charged nucleus with the delocalized electrons. Okay, going across the period now to transition elements like iron here. So transition elements, they're even smaller, and it's still delocalized this same 6 electrons, same as calcium here, but it's smaller than calcium. So therefore, the attraction is even stronger. The trend down the group. So going down the group, the melting point would decrease. The reason is because the same thing, it's called the metallic bond. The metallic bond would become weaker and weaker down the group. Okay, so the reason why metallic bond gets weaker down the group, it's because the size of the ions will increase down the group. So for example, if you have sodium compared to potassium. So as we can see here, this is closer to each other, so the attraction is stronger. This is further from each other, so the attraction is not as strong as when the ions are smaller. Okay, next, alloys. Alloys contain more than one metal. So in this picture, so I draw all the green ones, and then there's a yellow one here, which is larger than the others. We can enhance its properties. The reason is because this one is slightly larger here or different in size. This makes the alloy less flexible compared to the original green one. The reason is because there's a big one here, so it locks it there, makes it hard for the green ones to slide over each other and be flexible. So it's sort of locked there. So an alloy is less flexible than the original metal, but it still bonds via metallic bond because it's still the positive ions attracted to the delocalized electrons.